Okay, everyone, welcome to the first video lecture for Biology 1530. This is for Chapter 2. First, a quick note about these video lectures before we get started here for the course this semester. All of these video lectures, one for each chapter, or probably multiple ones actually for each chapter, will be available on Canvas for you to view at your leisure, whenever you like, that sort of thing. While you're viewing these, you should imagine yourself sitting in class and I'm giving you this lecture. This is what I would normally do for my in-person classes, but with the COVID-19 situation currently going on, I'm converting all my lectures to video format. So while you're watching these videos, you need to be taking notes, okay? Just as you would in any normal classroom during any normal in-person lecture. All right. So we start the class here with Chapter 2, and the reason for that is because Chapter 1 is sort of introductory in the sense that it covers, a lot of information we don't necessarily need for the course. It talks about the kinds of things you can expect in an introductory biology course, and because we're kind of time limited and that sort of thing, I've just never really gone over Chapter 1. Always start with Chapter 2. Now, Chapter 2 basically is about introductory chemistry. And so let me talk about the reasons for that. First of all, if you want to understand chemistry, you have to understand physics, okay? The physics determines the way that atoms behave when they come into contact with one another, determines how reactions play out, chemical reactions play out, that sort of thing. If you want to understand biology, you have to understand the chemistry because biology is a very specific type of chemistry, organic chemistry in particular. And so where chemistry is rooted in physics, biology is rooted in chemistry and also, by definition, in physics. So to understand biology, it helps to understand something about chemistry and physics. We're not going to focus so much on the physics aspect, although we'll see a little bit of that in chapters 8, 9, and 10. But mostly we're going to focus on, these first few chapters anyway, introductory chemistry. Not the complex stuff, the mathematical aspects you'll get in a traditional chemistry course, but the basics that you're going to need to understand how cells operate to a certain extent, okay? So chapter 2 then is titled The Chemical Context of Life, and it's going to deal with introductory chemistry. So, go back. So biology is the study of life, obviously, okay? Now living organisms, again, because biology is rooted in chemistry and physics, are subject to the basic laws of physics and chemistry. Now, organisms are composed of matter, okay? And matter is anything that has mass or weight and also takes up space. That's how we define matter. Okay, matter is anything that takes up space and has mass or weight. Now, matter is made up of chemical elements, all right? An element is a substance that cannot be broken down to other substances by chemical reactions. So, for example, carbon is an element. There's no chemical reaction that you can apply to carbon to break it down into some other kind of element. Okay, an element is elemental. You cannot break it down further through chemical reactions. Now, yes, it is possible to take an atom and split it apart through a thermonuclear reaction, for example, but that's not a chemical reaction. That's a different process entirely, okay, something we're not going to deal with. Now, we have another definition, compound, all right? A compound is a substance that consists of two or more elements in a fixed ratio, okay? Two or more elements in a fixed ratio. So for example, CO2. CO2 is a compound. It has one atom of carbon and two atoms of oxygen, always in a 1-to-2 ratio. By the way, if you don't see a subscript number on the right side of an element, that means only one copy of that atom. So one carbon atom with two oxygen atoms. Okay. The thing about compounds is that they have characteristics that are different from the characteristics of the elements that make them up. So CO2 has very specific chemical characteristics, and those characteristics are different than carbon by itself or than the characteristics of oxygen. Okay. So This gets us into talking about a very important underlying concept in biology and chemistry, and that is the concept of emergence, okay, or emergent properties. So the idea here with emergence or emergent properties is that you take simple things like an atom of carbon and two atoms of oxygen, which have their own specific characteristics. You combine them into a compound of CO2 and new properties emerge. So you've taken something simple, some building blocks like carbon and oxygen, combine them into something more complex, a molecule of CO2, and you end up with something that has new properties. So new properties have emerged. If you think about life, life is actually an emergent property. You take carbon, hydrogen, oxygen, and nitrogen, along with a few of the things that we'll see, combine them in very specific ways inside of a cell, and life emerges, okay? All right, so good example of how properties change. Take a look at sodium and chlorine. So here we have sodium. At room temperature, sodium is a very soft metal. You can cut it with a knife, as they're doing there in that image. Sodium, however, is extremely reactive, highly reactive. If you take and put a drop of water on that sodium, you will get a very violent heat-producing or exothermic reaction. And I'll show you a video of that here in a minute. So sodium is nasty by itself. You would not want to take a piece of sodium and chew on it. That would be a very bad day. Chlorine. Chlorine is this sort of yellowish-green gas you see in this flask here. Chlorine is extremely dangerous. If you were to breathe in chlorine, enough of it, it would actually burn the inside of the lungs and you would actually drown in your own fluids. Chlorine was one of the primary components of mustard gas that was used by the British, French, and the Germans in World War I. It would blind soldiers, it would destroy their lungs, just nasty stuff. So my point is that sodium and chlorine have very specific and literally very nasty properties on their own, but if you take one atom of sodium and bond it to one atom of chlorine, you get sodium chloride, table salt. Sprinkle that in French fries. I mean, it'll kill you in the long term in terms of high blood pressure, but it won't kill you right then and there the way sodium and chlorine have the potential to do. So clearly, sodium chloride has very, very different properties than either sodium and chlorine by themselves do, and so those new properties that we see with sodium chloride are an example of emergence. So let me show you a video. This is a YouTube video of what happens when you add sodium to water, just to show you how unique and violent its properties are. All right, so like I said, highly reactive material. And again, once you realize that, it's hard to imagine that sodium is part of table salt, but it absolutely is. Okay, so let's talk about elements then. So we said that elements are substances that cannot be broken down further by chemical reactions. I'm going to show you an image of the periodic table of the elements here in a little bit, and there are well over 100 elements on that table. Only 92 of those elements are actually naturally occurring. There are some elements that have been produced artificially through thermonuclear processes or reactions, that kind of thing. We certainly don't care about those. Those don't play a role in biology. But of those 92 elements that are naturally occurring, found in nature, only about 20 or 25% of those are actually what we call the essential elements. In other words, they play some role in our biology, okay? And of those 20 or 25%, it's actually only 4 of them, and they are carbon, hydrogen, oxygen, and nitrogen, that make up 96% of living matter. So as you sit in front of the computer and watch this video, 96% of your body weight is due to those four elements. We call them the Chon elements, CHON. All right, that means that they're very important in terms of the making up our bodies, making up our cells, making up the compounds that compose our cells. So the Chon elements are about 96% of living matter. Then we have about 4%, okay, most of the remaining 4%, and that for the most part is calcium, phosphorus, potassium, which is K, and sulfur. So calcium, potassium, phosphorus, and sulfur make up most of the remaining 4%. But then we have a very small amount left over not accounted for by these elements, and those are called the trace elements. They are elements that are present at less than 0.01% of body mass. All right. Okay, so let's take a look at a table that kind of breaks all this down. So you can see that up here in the top part, we have our Chon elements: carbon, hydrogen, oxygen, nitrogen. There you see the symbols for them and their respective percentages in terms of composition of living matter, but they add up to about 96.3% or thereabouts. Then roughly 4%, 3.7%, let's say, is made up of things like I said: calcium, potassium, calcium, phosphorus, potassium, sulfur, and then things like sodium, chlorine, and magnesium as well. That is about 3.7%, but then we have the trace elements down here, again, each one making up less than 0.01% of body mass. Really odd things: boron, chromium, cobalt, copper, fluorine, iodine, things like that. Things that you would maybe never expect to be in your cells, but they certainly are. And don't be fooled. Even though they're present at very, very, very low concentrations, 0.01% of body mass, let's say, they can still play very, very important and vital roles in cell function. And a deficiency of any one of them can potentially cause very serious problems, metabolic issues, and things like that. So they are very important. Okay, so now we're going to shift gears a little bit away from elements and talk about the atoms that make up these elements. Each element consists of unique atoms. A carbon atom has very distinctive properties compared to sulfur, compared to hydrogen, phosphorus, nitrogen, and so on. They're all unique. But while each atom is unique, all atoms are basically built of the same things, okay? It's just the arrangement of those parts, those subparts that we'll talk about, that makes each atom of each element unique, all right? So what's an atom? An atom is the smallest unit of matter that still retains the properties of the element. So you take a pile of carbon. Maybe it has hundreds of trillions of atoms of carbon in it. That pile of carbon has very specific properties, chemical properties, okay, density, mass, all these sorts of things. If you take a single carbon out of that single carbon atom will have exactly the same properties as the pile of carbon, okay? But when you look at the components that make up that carbon atom, they don't have those properties. So the atom then is the smallest unit of matter that still retains the properties of the element. All right, so what are atoms made of? Well, they're made of what are called subatomic particles, okay? Subatomic particles. Subatomic means smaller than the atom, or part of the atom. Now, there are a bunch of these, and physicists are seemingly always finding more as they smash atoms together in particle colliders and that sort of thing and figure out what's in them as the atoms break apart. All we really care about in terms of the atoms that are playing a role in our biology are three subatomic particles. We have neutrons, protons, and electrons. All right, now neutrons, as their name suggests, have no electrical charge. They're not positive, they're not negative, they're not anything. They don't have an electrical charge at all. Protons have a positive charge, and electrons have a negative charge. All right, now the thing about neutrons and protons is that they do actually have a measurable mass, which means they have weight, essentially, okay? Electrons effectively don't. Electrons are sort of thought of as being pure energy. For example, an electron weighs about 1/1800th of what a proton or a neutron weighs, all right? So we're going to start talking about the structure of atoms here in a minute, and one of the ways we describe the structure of an atom is through the mass of the atom, or the weight of the atom. And we're going to find that protons and neutrons make up the vast majority of the weight of an atom, whereas the electrons really don't contribute to the mass or weight of the atom much at all. Okay. Now, how is it that atoms are structured? Well, essentially, you can think of an atom, the structure of an atom is sort of like the structure of our solar system, right? So what's the structure of our solar system? We have the sun in the center, and the various planets orbit around the sun at various distances, okay? Well, think of an atom like this. So we have what's called the nucleus of the atom, and the neutrons and protons are found there. And then around that, you have electrons, and E minus means electron, and these various electrons orbit or move very quickly within their orbits at various specific distances from the nucleus, okay? Now, these electrons sort of form a cloud around the nucleus, and the reason why we say that is because the electrons are moving very fast. They're moving at the speed of light. Speed of light is 300,000 kilometers per second, or 186,000 miles per second. So imagine that, that's really fast. If you were in a spaceship and you were orbiting planet Earth at the speed of light, you could orbit the planet 7.5 times, 7.5 times in 1 second. So speed of light is extremely fast. It's like a cosmic speed limit, nothing goes faster that we know of. But these electrons are buzzing around in their orbits at the speed of light. So if you could see a photo or take a photo of an atom, you can't, they're too small, but if you could, you wouldn't see the electrons. You might see this sort of haze or cloud around the nucleus because they're moving so fast. So that area around the nucleus where you find the electrons is very often called the electron cloud. All right, so this is a figure from your textbook which kind of shows the atom both ways. Over here on the right, we have our nucleus with our protons shown with positive charge, neutrons shown here sort of in brown color with no charge. That's our nucleus. Then we have electrons here, okay? And again, those electrons are moving. So on the left, we see those electrons sort of shown as an electron cloud, or a cloud of negative charge, right? All atoms have this basic structure in terms of their neutrons, protons being in the nucleus, and the electrons orbiting around that nucleus. What makes each atom different, or each element different, is the number of these subatomic particles that they have. Carbon has a specific number of neutrons, protons, and electrons, and that is what makes carbon different from hydrogen, which has its own specific number of these particles, all right? So here's one way you can sort of think of an atom, right? I was talking about this in terms of, like the solar system. So you can see here in this large atom, the nucleus in the center, and then the electrons sort of orbiting around that. Now, any chemist who would look at this is going to say, no, that's not correct. And technically they're right. Okay, what's not correct about this is the electrons orbiting in those circular orbits around that nucleus. The reason that's not correct is actually because the electrons, all having a negative charge, they repel each other. So remember this, like charged particles repel each other. Oppositely charged particles attract each other. Remember, opposites attract, right? Okay, so as we're going to see in a little bit, these electrons aren't moving freely in those circular orbits around the nucleus like that. They're actually sort of locked into smaller volumes of space around that nucleus because they're all trying to repel each other while still being attracted to the positive protons in the nucleus, which keeps them there in their sort of respective locations or orbits around that nucleus, okay? But this is just meant to show you the overall structure of an atom, excuse me, with the electrons being on the outside of the nucleus like that. Okay, so how do we describe atoms or structure of atoms? Well, there's a couple of different ways or things that we can use to describe how an atom is sort of put together, all right? And the first thing is called the atomic number. The atomic number is simply the number of protons in the nucleus. How many protons are in the nucleus, all right? Okay. Then we have what's called the mass number. The mass number. The mass number is the sum of protons and neutrons. So if we know how many protons there are and how many neutrons, we add them up, that gives us what's called the mass number. Okay, it's an approximation of the weight of the atom, or the atomic mass. The atomic mass is the atom's actual total weight or mass. Okay, and we can approximate that, arrive at an approximation of it, an estimate of it, through mass number by simply adding up number of protons and neutrons. Okay, and each atom, or each element rather, its atoms will have a unique atomic number and unique mass numbers. All right, so let's take a look at, well, I kind of forgot a slide there. Okay, so when you look at the periodic table, what you're going to see is that every element has its own specific mass number. All right, so for example, if I were to show you carbon, all right, so first of all, carbon is going to be in a square like this, and in the center you'll have the symbol for carbon, which is C. Okay, the atomic number is usually on top, either on the right-hand side or left, and carbon's atomic number is 6. That means carbon has 6 protons, right? On the bottom, typically you'll see the mass number, and carbon's mass number is 12.01. All right, so 12.01 what? Daltons. We measure mass of atoms in Daltons. Atoms are so small, it doesn't make sense to try and measure them in something more common, like a gram, for example. The number would be so small, it just wouldn't make any sense. You wouldn't be able to wrap your head around it. It just wouldn't have any meaning. So a new unit of measurement was developed called a Dalton, and that's what that number is 12.01 Daltons. Okay. Now again, that's our mass number, right? So if you add up number of protons and neutrons, you get 12. That's because carbon has 6 protons and 6 neutrons. 6 plus 6 gives you 12, and that 12 is an approximation of the actual mass number of the atom, 12.01. All right. Now, that means we have in carbon we have 6 protons and 6 neutrons. So how many electrons? Well, also 6. All right. So as a general rule, the number of neutrons equals the number of protons, which equals the number of electrons. So carbon has 6 neutrons, 6 protons, and 6 electrons. And again, because electrons have almost negligible mass, we don't include them in the weight of the atom. We don't need to worry about them in terms of mass number. All we need to worry about there is adding up number of protons and neutrons, and that gives us an approximation or an estimate of the atomic mass of the atom. All right. What about nitrogen, let's say? So nitrogen, right there, N, has an atomic number of 7, so 7 protons. And if you add number of protons, which is 7, to number of neutrons, which is 7, you get a mass number of 14. And nitrogen's mass number is 14.01. So there you have it. And again, it also has 7 electrons. Okay. All right. So that's the case with most atoms on the periodic table. Now, it's more complicated than that because it turns out that most atoms come in various different forms as well. All right. And these various different forms of these atoms that we're going to talk about next are referred to as isotopes. Okay. So an isotope is an atom, or isotopes rather, are atoms of an element that differ in their number of neutrons. So isotopes have different numbers of neutrons than the normal form or the non-isotopic form of the atom. All right. So, for example, there's a common isotope or a relatively common isotope of carbon. It's called carbon-13. Okay, now that 13 is the mass number. All right. So, I said normal carbon has a mass number of 12, right? 6 neutrons, 6 protons. with isotopes, you know that they differ in the number of neutrons. So what would you have to do to get carbon's mass number up to 13 in an isotope? You'd have to add one more neutron. So carbon 13 has 6 protons and 7 neutrons. That's where the 13 comes from. It's a slightly different version of carbon in that its number of neutrons differs. It has 7 neutrons, not 6 like normal carbon, and therefore we call it carbon 13. There's also another isotope of carbon, carbon 14. Carbon 14 has 8 neutrons and 6 protons. Okay. Now, there are lots of different, there are even more isotopes of carbon than this. There are more isotopes of other atoms as well. But one of the common features of isotopes is that they're very often radioactive, which means they give off energy, radioactivity. And the reason for that is because an isotope having a different number of neutrons and protons, that situation makes its nucleus unstable. And here's the first rule about nature. Things in nature tend to go from unstable to stable. Nature likes the things to be stable, and so it'll take unstable situations and convert them to stable situations. We're going to see that throughout this course. Okay, so if you have carbon 13, for example, which has 7 neutrons and 6 protons, that's an unstable nucleus. It wants to convert back to carbon 12, the more normal form, the stable form of the atom, and the way it does that is by giving off that extra neutron over time through radioactive decay. All right, it gives off radioactive energy, and eventually that extra neutron sort of decomposes or breaks down, decays, let's say, until the carbon goes back to carbon 12. Now, it takes a certain amount of time for that to happen. The amount of time needed for 1/2 of a sample of, let's say, radioactive carbon 13 to decay back to carbon 12 is called a half-life. Okay, half-life. Write that right there. The half-life is the time it takes for 1/2 of a sample of a radioactive isotope to decay back to the normal form. Carbon's half-life is about 5,700 years, I believe. So if you had a pile of carbon, carbon 13, a fresh, brand new pile of it, in 5,700 years, half of it would convert back to carbon 12. Then that half that remains, in another 5,700 years, half of it would decay back to carbon 12, and so on. So every radioactive isotope decays at a specific rate, what's called its half-life. Some half-lives are relatively short, like carbon, for example. Some, like uranium-235, are in the hundreds of millions of years. And nothing causes the rate of decay of a particular atom, radioactive isotope, to change. Not differences in pressure, temperature, pH, nothing. It happens like clockwork. It's totally predictable. Nothing phases it. And every isotope will break down or decay at different rates. That means that we can use isotopes, radioactive isotopes, as tracers. Okay. These are often used, isotopes are often used as diagnostic tools in medicine. They can be used to track atoms through metabolism. They can be used in combination with really sophisticated imaging instruments. There's one in particular called a PET scan, a positron emission tomography scan, and it's a very useful tool for looking for cancers. You can think of it kind of like a CAT scan, but not quite. So imagine that you've been diagnosed with cancer and they want to find how extensive the cancer is throughout the body. They can actually inject an isotope into a patient. That isotope, for reasons I don't quite understand, will adhere to the cancer cells only, and then because the isotope gives off radioactive energy, the machine can detect that. They put you in the PET scanner, and it shows you, or the doctors rather, where all the cancer is because they're now highlighted, they're glowing because of the radioactivity. So it's very useful. Isotopes are also how we conduct radiometric dating. Have you ever wondered how, paleontologists can dig up a bone or something, a fossil, and know how long it's been since that animal died, or how long a piece of charcoal has been sitting in a fire pit in a cave in France, for example? It's because these organic materials or the rocks around them have known amounts of radioactive isotopes in them. And by, for example, looking at, let's say, a piece of charcoal buried in a cave that used to be part of a fire pit maybe 15,000 years ago, we know how much carbon-13 or carbon-14 there was in that wood when it was living as a tree, and you can measure the amount that's left, and by back calculation, we can determine how long it's been since that tree was chopped down and burned as a piece of wood and ended up as a piece of charcoal in that fire pit. It's extremely accurate. And again, it works because nothing changes that rate of decay. All right. So next thing we're going to start to do is talk about or get into a discussion of how it is that atoms behave, or why it is that atoms behave the way that they do. And this is really important for ultimately understanding chemical reactions. And understanding chemical reactions is important for understanding how cells work, and so on up the line to understanding how you work, how ecosystems work, all the way up. All right. Well, if you want to understand how an atom behaves, you really have to understand the electrons. Okay, the electrons are sort of where it's at in terms of understanding behavior of atoms or reactivity of atoms. Now, before we talk about electrons, we have to understand something about energy. Because again, like I said before, you can sort of think of electrons as just pure energy. So what is energy? Well, energy is the capacity to cause change in something, okay? If I pick up the mouse that's sitting next to my computer right now and move it across the table, that's energy that I applied to change the position of that mouse, okay? The energy I applied caused change. Change in what? The position of that mouse. Now, energy comes in a variety of forms. We have potential energy, for example. Potential energy is the energy that matter has because of its location or structure, okay? So, you can think of a pen sitting on top of a desk, maybe precariously balanced on the edge of that desk, as having high potential energy, gravitational potential energy. If you nudge that pen, it's going to fall to the floor. And as it does so, it gives off energy, because that potential energy it had on top of the desk is converted to another type called kinetic. Kinetic energy is energy of motion. All right, we'll get into all that a little bit later on, but the point is the potential energy of that pen is energy that that pen has because of its location, stored at elevation above the floor. You can also have potential energy stored in the structure of something. So when you get in your car and you flip on or turn the ignition, what you're doing is causing a chemical reaction in the combustion chamber that's combusting or burning fuel, gasoline. Well, there's lots of energy stored in those molecules of gasoline, and that's potential energy that's stored in the structure of those molecules, okay? So potential energy is the energy that matter has because of its location or its structure. All right. Now, the electrons of an atom differ in the amounts of potential energy that they have. And an electron's state of potential energy is called its energy level or its electron shell. So let's take a look. All right, another figure from your book. So let's imagine we have our atomic nucleus here. So our neutrons and protons are there, and we have electrons in various different orbits, let's say, or energy levels or energy shells around that nucleus. All right. So let's say we have an electron here in this first shell. If we apply energy, say light or heat, to that atom, we can cause that electron to bump out to the second shell, okay? If we apply enough, we can make it bump out 2 shells to the third shell, for example. And as long as that energy is applied, that electron will stay there. Or we turn off the source of energy, that electron will then fall back to its original position, and the energy that was absorbed to make it bump out, that energy is then lost. It's given off. This is exactly why the hood of a car heats up when it's in the sun, for example. So think about the hood of the car, right? It's made of metal. There are atoms in the metal. There are atoms in the paint covering the metal. When sunlight hits those atoms, the electrons of the atoms bump out to higher energy levels and absorb energy. So they go from low potential to high potential, and then they fall back down to their original positions and they give off that energy as heat. And so the hood of the car heats up. That's an example of energy transfer. That right there, as simple as it sounds, is the whole basis of photosynthesis. This is how chlorophyll molecules in plant cells capture solar energy. It's all based on causing electrons to do this very thing, okay? All right. So, in order to understand why it is that atoms behave the way they do, you have to understand what's called electron distribution. In other words, how many electrons does an atom have, and where are those electrons found, okay? In what shells, how close to the nucleus of the atom, that kind of thing. The chemical behavior of an atom is determined by the distribution of electrons in the electron shells. And the periodic table, which I'm getting ready to show you, of the elements shows the electron distribution of each element. So let's take a look. This is an abbreviated version of the periodic table. It just contains the first three rows, okay, or periods as they're called. And so, first of all, what you see up here in the top left is hydrogen. Now, hydrogen is a unique atom. For one, it only has one proton and one electron. Hydrogen does not have a neutron. It's made of one proton, which is found there in the nucleus, and one electron around it. Now, that electron, because it's the only electron, is free to orbit around that nucleus in sort of a spherical orbit. It can go wherever it likes, as long as it stays around that nucleus. Why does it stay around that nucleus? Because it's attracted to the positive proton. Remember, opposite charges attract, right? Okay. Now, what you know about hydrogen is that it's very reactive, okay? The Nazis found this out the hard way. Back in 1938, they built the Hindenburg blimp. They sent it over to New Jersey on sort of a propaganda tour, and they filled it with hydrogen because hydrogen was cheaper than helium. Well, something happened, lightning strike, spark, whatever, no one knows, and the thing blew up in New Jersey. And if you've ever seen a video of this, it's quite dramatic. You ever heard the phrase, "Oh, the humanity"? Well, that's what the guy was saying, the newsreel guy was saying as he's watching this blimp explode on the tarmac at an airport in New Jersey. Anyway, hydrogen is extremely volatile, very flammable, okay? Now, if you go over here to the right, you have helium. Now, helium is very similar to hydrogen, has an atomic number of 2, which means, again, 2 neutrons, 2 protons, and 2 electrons. Yes, helium does have neutrons. So in its nucleus, it has 2 protons and 2 neutrons, and now 2 electrons orbiting around that. Why should the Nazis have used helium? Because it's non-reactive. It does not participate in chemical reactions. It will not explode the way that hydrogen will. But it's very similar, isn't it? Just has a few more subatomic particles, okay? All right. Well, here's the first rule about electron distribution. The first electron shell that you see here in the case of hydrogen and also here in helium, it can only hold 2 electrons. That's it. Now, why is that important? It's important to chemical reactivity because the more complete the outer shell of an the outer shell of an atom is, the less reactive that atom is. So this first shell can hold only 2 electrons. Well, hydrogen's shell is only 50% complete. It has 1 electron. Therefore, it's reactive. Add 1 more electron plus a neutron and proton, you get helium, but the point is the electrons now, the 2, make that shell full, complete. So helium doesn't react. All right. Now, what if you have a third electron and a third neutron and a third proton? Well, then you have to come down here to lithium. Lithium, atomic number 3, has 3 protons, 3 neutrons in the nucleus, and here you see 3 electrons. 2 in the first shell, well, it's full, so the third electron goes in the second shell, right there. Now you see 2 shells. Now, this introduces us to what's called the octet rule. Octet means 8, right? Octet. The octet rule says that the second, third, and I think even the fourth shells can hold a maximum of 8 electrons. So, lithium's second shell, or its outermost shell, which is also called the valence shell, that's the outermost shell, only has 1 of the 8 electrons it could hold. Remember, the fewer the electrons in the outermost shell, the more reactive the atom is. Lithium is highly reactive. But you go to the right, beryllium, you add 2 electrons, It's now 25% complete, the valence shell is. It's a little less reactive than lithium. Go one to the right, boron, you add one more electron, now we're up to 3 in the outer shell, 5 total, less reactive. Carbon has 6 electrons, 2 in the first, 4 in the second. Outermost shell is 50% complete, still reactive, but not nearly so much as lithium. Every step of the way, we add one more electron until you get over here to the right, and now you see neon, right? So atomic number 10, that's 10 protons, 10 neutrons, and 10 electrons. Do the accounting of the electrons, 2 in the first shell, 8 in the second. Valence shell is full, isn't it? Neon, like helium, is non-reactive. So is argon below it. Everything in the right-hand side here is called the noble gases. Helium, neon, argon, radon, krypton, and so on. These don't react with anything. This is why we use helium in birthday party balloons that are around lit candles on cakes, not hydrogen. It's why we use neon in neon signs, not hydrogen, because it won't explode. It just glows. Phosphorescence gives off light and makes the Budweiser sign light up. Now, come down to the left, sodium. I showed you a video of sodium earlier, highly reactive. Why? Well, sodium has 11 electrons. You see the atomic number is 11. That's 2 in the first, 8 in the second, that's 10. 1, the 11th, left over for the third shell. That third shell is only 1/8 full. Sodium, highly reactive because of that. It reacts in much the same way lithium does because they have the same number of outer shell electrons. Beryllium and magnesium have the same number of outer shell electrons. They react in a similar way. Boron and aluminum react in a similar way. You get the idea. Okay, so the point is that the periodic table here is arranged, or the elements are arranged on it through or as a result of electron distribution, right? You have one electron in the outer shell here. Every step to the right adds one more, and the valence shells become progressively more complete until we get to the noble gases where they are complete. Okay. And it turns out that in these first 3 periods of the periodic table, this is where most of the elements are that are the essential elements that are important for life. Okay. So we don't really care about anything, much of the atoms, in other words, that have 4 shells or so on down the line in the periodic table. Those are not atoms that, by and large, play any role really in biology. Now, elements like helium, neon, and argon on the right-hand side, noble gases, them being non-reactive, they are referred to as being chemically inert. They don't react. So, of course, they don't play a role in our biology because they don't react with anything. Okay. All right. Another important aspect about electron distribution here. I said before that nature tries to make things more stable, correct? Yes, okay. Well, how do atoms become more stable? If lithium is extremely reactive because it only has 1 electron in the outermost shell, that means it's unstable. It can become more stable by adding more electrons, by completing its outer shell. And there are various ways that atoms can do that. One of the primary ways is through forming chemical bonds, all right? So if you want to understand how a DNA molecule is built, or a sugar, or a protein, or a fat molecule, for example, you have to understand how it is that the atoms that make up those molecules bind to each other. Why do they bind to each other? And why do they bind to each other in the arrangements that they do to give that molecule its overall 3-dimensional shape, which then gives it its function? It's a result of the atoms wanting to complete their outer shells. Okay? Carbon, for example, having only 4 electrons in the outer shell, its valence shell, outermost shell, is only 50% complete. So it could bring on more electrons through bonds with other atoms and, in effect, complete its outer shell. The point is, for now, and we'll see more about bonds here in the next video, the second video of this chapter, is that the number of electrons that an atom needs to take on to complete its outer shell tells you how many bonds it forms. So look at carbon. It has 4 outer shell or valence electrons, correct? 1, 2, 3, 4. It would need to bring in 4 more electrons to complete its outer shell. That means it forms 4 bonds. So the valence that you see there, that term, is also referred to as, or refers to, I should say, the number of electrons an atom would need to bring in to complete its outer shell. Carbon's valence is 4. Nitrogen's valence is 3. It has 5 electrons in the outer shell, would need to bring in 3 more. Its valence number is 3. That tells you that nitrogen forms 3 bonds. Oxygen, having 6 electrons in the outer shell, has a valence number of 2. It would form 2 bonds. All right? Okay. So I think this is a good place to stop. I'm going to try and keep these videos at around 40 or 45 minutes because of file size issues and that sort of thing. So I'm going to stop here, and we'll pick up with this more in depth in the second part of this video lecture for Chapter 2.